Okay, today we talked about irrotational flow, also known as potential flow, because of the use of a velocity potential in the description of the velocity field. The basic condition for irrotational flow is that the vorticity is zero, which means that for a velocity field given by components u, v, w, we can define a velocity potential phi of x, y, and z, where each velocity component is equal to the component of the gradient of the velocity potential. So u is d phi dx, v is d phi dy, that's a phi there, and w is d phi dz. Who knew phis were so hard to draw in this app? We started then talking about the basic building blocks for solutions. When we apply mass conservation, the continuity equation, we arrive at Laplace's equation, which means that the Laplacian of the velocity potential is zero. That's the equation that we then need to solve, and we're going to do it through a method of superpositions. Today, then, in the last bit of lecture, we introduced four basic solutions that I'll just outline here. We have one, the source, or the sink. I'm just going to sketch it for this review. It's radial flow emerging from a source, in this case from the origin. If it was a sink, the flow would be reversed and towards the origin. Okay, so we have radial flow outwards. It decreases with distance, so you have smaller velocities as you move away. That's required by mass conservation. Now the second basic flow is uniform flow. Very simply, uniform flow is just flow from left to right of uniform magnitude u0. Nothing more to that to be said. The third is the vortex, the irrotational vortex. This is the counterintuitive one where we have a flow that's revolving around the origin, but the vorticity is zero. So if here's our origin, the basic feature of the irrotational vortex is that the velocity is highest near the origin, and as we move away from the origin, the velocity decreases. And it decreases with 1 over the distance, and that's what preserves the irrotational nature of the flow. Finally, very end of lecture today, we talked about the doublet. Had someone come up at the end of lecture and ask about whether it's analogous to a dipole. It absolutely is, for those of you that remember your electricity and magnetism. The doublet consists of a flow which has this sort of figure 8 character, with flow exiting the origin to the left and entering from the right and extending off like so. Now, the doublet on its own, it has a singular point right at the origin. The doublet on its own does not have a great physical interpretation, but what we'll see on Wednesday is that when we combine the doublet with uniform flow, we create a flow pattern which is flow around a cylinder. If we add a vortex to it, then it can be flow around a spinning cylinder. So that's the kind of solutions that we're going to be able to develop now with these tools.